Good morning.
Good morning.
Good morning.
Okay, good morning, everyone. Probably it's time to start our lecture. So let's start with sharing a screen. Okay. Okay. So my name is Professor Ignacy Diliba. Um, I'm at building C3, Rome. I don't think it will be required for you at this lecture, but nevertheless, I provide this information. And the most important, all the data you can find at my web page. Tilda and I. So please visit this web page and you can find all required information. I mean, for example, some grading system or contents of the lecture, so subject list also. Okay, let's say a few words about office hours. They will be announced probably in 1 or 2 weeks, but probably I'm planning before and after this lecture. Okay, and probably you should somehow um, you should prescribe presence at the office hours, and probably there will be some slots, probably 10 minutes long. And before entering the office hours, you should prescribe appropriate time, just not to make some problems when a few people can enter at the same time. Okay, and what's more, maybe there are some questions concerning the data I've provided to you. So there are some questions. Maybe a few words about grading system. Of course, all the details are given at this web page, but roughly speaking, we have a lecture plus lab session. And they start probably 4 or 5 weeks later. Okay, why? Because we need some material required for lab sessions, and the final grade is just plus. But of course, these and these marks should be positive. And what is more important, from lecture we have written test. And it is just to pass or not this. The minimal mark will be 3 in Polish scale. But those who pass this test and want a higher note, so they will will be asked to answer some questions orally. Okay, so probably it is all for this organization job. So right now I can start the regular lecture. So before this, I will provide some general information because I reschedule the subject list a little bit. Why? Because we need some data to start lab session. Therefore, traditionally we should start with some history, some classification of robots, but probably we will move this the introductory lecture to later time, and immediately we start with some real robotics task. But generally, we will talk about 2 classes of robots. The first one is manipulator. You can see manipulators at factory floors. But of course, some terms should be introduced here. I mean, such manipulators is composed of links. Here you can see links here and here. Between links, we have joints. And at the joints, a motion is performed. Links just transmit this motion. A special point is here. It is called end effector. Why this point is special? Because we act on environment of this robot, and we impact the surrounding of the robot with this point. So our first goal is to control this point. Why? Because, for example, and at end effector you can find a camera which gives information about visual data, or for example, here at end effector you can see gripper when a robot catches something. So the most important point we want to control it is via end effector. Okay. Of course, we need to have a global system which is, let's say, X, Y, and Z. And usually this global system is fixed to the base of the robot, and it is constant. Yes, why we want a global system? Because all position, orientation, etc., are related and are expressed in this system. So at very first few lectures, we will consider just modeling and some task concerning the manipulators. Okay, our second class of robots will be mobile robots. Okay, and a few words and a few lectures will be devoted to modeling and controlling such manipulators. Okay, and after, so the first part, the very big part of our lectures can be entitled modeling of robotic system. But of course, the modeling is required for other purposes. For example, for planning a motion. So, for example, if we model a manipulator, we can also define some tasks. For example, how to move the end of effector along a given path. Okay, so we want to control this point, but of course you can easily guess that if we want to move end effector along a given curve, we can impact this motion via joints. So the primary controls are applied at joints. We can shift or rotate joints. Okay, so we have motion planning, and probably 2 lectures will be devoted to motion planning, maybe even more. And the final is control. Control, probably controlling a manipulator. Please notice that planning means we are planning something. Okay, so we predict that some motion should be performed, but from different reasons, for example, a noise or inaccuracy in modeling. So probably you can encounter an error, and therefore we need the final robotic task, I mean controlling. So the primary goal of controlling is just to define some error, and we want to propose a control law which gives us that this error goes to 0 as time goes to infinity. Okay, so we just want to control this motion. So you can see that planning in ideal case is along this path, but at control stage we can assume that due to some reasons we start a motion from this point, and all principles of controlling is how to provide some controls which try to, like this, for example. Okay, so finally we want to have the error tends to 0. Okay. By the way, all the notes and all the notes presented here will be available to you. Probably I will give it via ePortal. Probably in PDF form. Okay, probably it will be the best solution for you and for me as well. Okay, so let's start with some introductory material. We need to recall some basic facts from elementary mathematics. So Of course, it is very, very basic, so don't afraid of this. So let's start with a real line. Okay, it is traditionally described like this, real line. And our primary question is where we are on this line. So before describing this, we need to have what? So let's. I will try to ask you and help me to because I want this lecture to be vivid. Therefore, please actively participate in this lecture. So what we need to have if I want to, for example, describe some point at this line. So
we need a zero as a
zero.
reference.
Okay. So we need some point, reference point, which is zero. So we have zero. Okay. What more?
One
What?
number. One number that would be an index.
I don't understand.
He means the unit, the one.
Okay. We need a unit. Okay. So please notice that here I have a line and also an axis. Okay. So this arrow shows us positive coordinates something, and here negative. Of course, we need a unit. Okay. Let's say described by I vector. Okay. And if I take a unit I, so for example, this point would be probably twice I. Okay. So instead, if the unit is fixed, so I can describe this point just saying 2. Why? Because I assumed a unit, and this point reflects a vector. Please notice that it is a position, but also a vector from 0 till this point. Okay, so 2 is just a coordinate in this system. So using I as a measure. But let's try this. If I will assume that I will be like this, okay? So let's forget the previous notation. And if I would be like this, so this point would have a coordinate of what? 1. Okay, but 2 would be here. Okay, so as you can see, coordinate is just expressing how many units can be assigned to some fixed point. Of course, quite natural is that unit is just a unit. So we can say versor. Versor, it is a special vector of length equal to 1. Okay, so versor. So please take into account this term. Okay, so here we have a real line. So it is one-dimensional object. But of course, you can take two-dimensional object, okay, like this. And here we have I, unit length, here J, and traditionally is describe X and Y. And of course, you can see that this point can be expressed. This point is described also as a vector from 0 to this. So probably this point, let's call it P. So it is twice multiplied by I, like this, plus 1 of J. So coordinates of P are 2 and 1, as you can see, 2 and 1. So if versors of axes are fixed, so instead of describing points or vectors in this full form, we can shrink the description, and we will operate with coordinates in this system. Of course, here we have two-dimensional object, but generally we will work in three-dimensional space, and it is probably the biggest space we encounter at this lecture. So we have X, Y, and Z. Please notice, like here, so the axes here are perpendicular to each other. Okay, why? Because it is useful to describe, but probably at mathematics you also found that, for example, such vectors will span a plane, of course, but don't mind about this. So here we have three axes. All of them are perpendicular to each other. Okay. And here we have versor I, here we have versor J, and here we have versor K. Okay. And each point in this frame can be described by some coordinates. So P will be, let's say, alpha 1 multiplied by I plus alpha 2 multiplied by J and alpha 3 multiplied by K. And coordinates of P are alpha 1, alpha 2, and alpha 3. Traditionally, in robotics, we describe a versor in column form. So, like here, I have vectors with three components, and they are arranged in column form. If I want to have a row description, so I will write down alpha 1, alpha 2, and alpha 3, and T means transposition. You know this from elementary mathematics. Okay, so where is our first problem? We will operate in a three-dimensional space, so in R3, and our first goal is to describe some transformation. Let us assume that I have such a coordinate system. Let's call it zero coordinate system with some versors I0, J0, and K0. Okay. And I will attach, and the system is anchored at a point, let's say O0, so it is the base of this frame. And I will try to have another coordinate system also attached at this point. And I will mark it in green. Okay. It is another system. Here I will have I1. Here I have J1, and here I have K1. Okay, so you can see I have two frames attached at the same point. And what is our first task? Let us assume that I have a point here, P. So you can easily guess that this point P can be expressed in zero system, okay? So this point at zero frame, P will have coordinates P0x, P0y, and P0z, okay? But also this point can be viewed from the perspective of the first frame, okay? And at the first frame, this point P will have different coordinates, probably P1x, P1y, and P1z. And we will try to find relationship between the two coordinates. But before doing this, we need to recall some basic facts from mathematics. So let's assume that I have a vector x with xy, x2 and x3. Why? Because we work in a three-dimensional space. And let's have another vector y. Okay, so probably you know some operations. I mean inner product of vectors. So it is described like this. Sometimes it is described like this, but probably we will describe in the simplest form like this, okay? So what is the inner product? We need to have two arguments. As you can see, it is the first argument, the second argument, and we have also result of this operation. So the inner product is defined like this. X1 plus X2 y2 plus X3 y3. Okay, so you can see we multiplied appropriate coordinates and sum up this. So from mathematical point of view, inner product is transformation R3. So the first argument is three-dimensional vector, as you can see. The second argument is three-dimensional vector. And as a result, what we obtain, what is this? It is a vector or something else?
Scalar.
Scalar, but scalar is real, yes? So inner product takes two vectors and sends it into a scalar. Okay, so basic facts about inner product are the following. What will happen if I change position of x and y? What will happen?
It will Yes.
It will be the same. This property is symmetry, which means that I can change the ordering of arguments, but results remain the same. But what is important from a robotic perspective is some kind of interpretation, but maybe not now. What is this? X and X. If I plug twice X, so probably from this I will obtain x1 square plus x2 square plus x3 square. If I take a square root of this, so what is this?
The length.
The length. Okay, it is the length of vector x. Traditionally, length of vector is described with this symbol. Okay, so the length of vector is square root of scalar product of x and x. So twice we take this. Okay, so let's take back to this interpretation. Having defined the length, I can describe scalar product like this. Okay, so what is this? Let's make a small picture. I have x vector, I have y vector, and scalar product is just the length of this vector multiplied by a length of this vector multiplied by cosinus of angle between the two vectors. Okay, so it is here. So let's analyze this equality, for example. If I have x and x, so I will obtain x multiplied by x multiplied by cosinus of 0. Why? Because the angle between x and x is 0. So the vectors coincide. And this is equal to 1. So as you can see, x is x squared. If I take square root, I will obtain the previous relationship. Now, this identity is very important. Why? So I will mark it. This identity is very important. Why? Because it is very useful in checking whether vectors x and y are perpendicular to each other. If x and y are perpendicular to each other, so the angle between the two vectors is equal to, let's say, 90 degrees. So cosinus of 90 degrees is equal to 0, okay? So it is a very useful method to check whether vectors are perpendicular to each other or not. So we need to just calculate inner product, and in this way we will obtain the answer, whether the vectors are perpendicular or not. So the other useful transformation is vector product. Probably you also know this notation. Vector products is denoted by the very small x. Of course, this sign isn't argument x, but just as a cross. Sometimes vector product or cross product. And vector product is what? Also, we have two arguments. We have two vectors, but the result is also a vector. So here we have R3, so it is X, R3, and finally we will obtain R3. So how components of this vector are computed? Quite simple. It is, I will x1, x2, x3. I put coordinates of the first argument here. I put coordinates of the second vector here, and I will determinant of these. So I will obtain x2 multiplied by y3 minus x3 multiplied by 2, okay, plus j. Of course, it is just expansion with respect to the first row, and you should be careful here because from this we take x3 j1 minus x1 y3 plus k x1 here in natural x2 minus x2 by 1. So finally, as you can see, if I have x and y, the result is the first component is x2 y3 minus x3 y2, as you can see. The second component is x3 j1 minus x1 y3, and the third component is x1 y2 minus x2 y1. Okay, as you can see, I have one argument, three-dimensional vector, the second argument, three-dimensional vector, and based on the two vectors, appropriate composing components of the vectors, I will obtain these. Okay, but of course, it is very useful geometrical interpretation of these. So I have here x, I have here y vector, and how this vector, resulting vector, is related to this. Please notice that if we have two vectors, so the two vectors, of course, when they have length not equal to 0 and they aren't collinear, they span a plane, okay? It is just a plane, because any two vectors, non-zero vectors, not collinear, span a plane. But the resulting vector is perpendicular to this plane. So I will x is perpendicular to the first argument and perpendicular to the second argument. Okay, but of course vector have a length. So what is the length of this vector? It is quite simple, because it is length of x multiplied by length of y and multiplied by sinus of angle between x and y. Okay, very similar, but as you can see in inner product we have cosinus here, but here we have sinus function. Okay, and okay, and of course, so it is the length. So how length is this vector? But of course, we need also describe orientation of this vector. So very important in robotics is so-called right-handed rule. So please notice that if I rotate, I will take right hand, and if I rotate X towards Y, so in which direction the screw goes? As you can see, probably it's up, okay? So if I rotate this towards this, so right-handed screw would have like this. So the sign is here. Okay. Of course, let's illustrate a right-handed rule like this. Okay. So please experiment with yourself. Let us assume that I have an axis with arrow goes up. Let us assume that I have a thumb like this, okay, and it goes up, okay. If I, of course, it is right hand. Please experiment with yourself. If I move counterclockwise, okay, like this, so I will move up, okay. So it presents me, okay, like this. It is just right-handed rule. Here also you can see, based on right-handed rule, you can describe, for example, which rotation is positive or negative. Of course, positive would be if I move from here to here, so the rotation would have a sign plus, or from here to here, minus, okay? But of course, we will train it later on very frequently. Okay, so having defined the inner product and cross product, we are in position to go back to this picture and try to establish relationship between coordinates in the first and zero frame. So let's describe this. So I will recall here I have zero. I will not describe axes versor. Why not? Why? Because I don't to have a mess here. We have zero frame and the first frame, and I have P, so some point. And from perspective of zero frame, as you remember, this point P can be described like this: POX multiplied by I0. So versor along x-axis of zero frame plus P0Y J0. Here we have I0 J0 K0 plus POZ K0. So here, this point P appearing here is viewed from the perspective of zero frame, but also this point P can be described from the perspective of the first frame. So you can easily guess that it will be P1X I1, because here we have in other versors. Why? Because they belong to the first frame. So they will be described like this: P1 Y J1 plus P1 Z K1. Okay, but as you can see, the same point It is described from perspective of one frame and the second frame. So what I will done here, let's multiply this and this by I0, say. So of course, I will multiply it like in a scalar product. So what will happen in this case? POX I0 I0 plus POY J0 I0 plus POZ K0 I0. Okay. And of course, because P and P is the same point, so I will write down P1x, I1j, because I multiplied this equation and this by the same vector, P1y j1 I0 plus P1z k1 I0. Okay. So nothing strange can happen, but what can I say about this? It is a scalar product of I0 and I0. So what is the value of this?
The length of I0. So if it's a unit vector, then
exactly. Okay. Please write me on chat who answered this question. Okay. So using property of inner product, we have I0 I0 cosinus of angle I0 I0. This angle is 0, so the cosinus is 1, and I0 is unit length, so 1 and 1. So finally it is 1. But what about this? You remember what we said before? We've mentioned that inner product is quite useful in checking whether some vectors are perpendicular or not. According to this zero system, what we can say about J0 and I0?
They are perpendicular, so it's 0.
Okay,
Oh, exactly. Okay. So the person who answered this question also should write down on chat his name or her name. Okay, and also here, because K0 is perpendicular to I0, so it is 0. So finally, we obtain what? So on left-hand side, we have POX multiplied by 1, and here 0, 0 is equal to P1x I0. I will write it down maybe in a little different form. Okay, because please notice that this is just a scalar value, because scalars can be multiplied from left or right. So I'll be write down just like this: I1, I0. Why? Because you can see in a while what will happen. P1y, yes, plus K1 I0 P1z. Okay, so finally I'm just multiplying the two equalities by I0. I've obtained such a nice equation. Okay, so what's now? Now I will instead of multiplying by I0, I will multiply by J0. And what will happen in this case? I will not repeat this form. Probably you can easily guess what will happen here. So in this case, what will be here? P PO
Y.
Y, exactly. Yes. Here, what will be, here was multiplied by I0, as you can see.
J1, I0.
Oh, yes.
Or the other.
And P1X. Please notice that mnemotechnic rule is quite visible here. Yes. Instead of I0, I plug J0, P1Y plus K1 I0 P1Z. You can probably guess what will happen next. I will multiply this not by I0, not by J0, but I will multiply by K0. And the final form will be POZ. So these coordinates will be selected, and you can K0 P1X plus J1 K0 P1Y plus K1 K0 P1Z. So finally, I've obtained 3 equations. I don't like 3 equations. I will prefer 1 equation. So please notice that here, so what is this? So it is just P0. Yes, P0, it is POX, POY, and POZ. So P0 is what? I will plug here in a matrix form. So I will put here P1X, P1Y, and P1Z. So the matrix here will be 3 by 3, because here we have 3 by 1, 3 by 3, and 3 by 1. So everything is okay. So the first equation here, POX is equal P1X multiplied by this. So I must plug here I1, I0. So it is a scalar product of what? Of I versor from the first and the from the 0 frame and the first frame. Here we have J1 I0 and K1 I0. As you can see, so it is quite easy. I1, I1. Here we have J0, K0, J1, J1, J0, K0, K1, K1, J0, K0. Okay, so finally, I will write down in this form. As you can see, this is just P1. So finally, PO is equal R10 P1. So this matrix R10 is described by this. This matrix is composed of inner products of appropriate versors. The one belongs to 0 frame, the second belongs to the first frame. And it is very nice formula. Okay, and what the formula says? The formula says, if I have coordinates in the first frame, if I have versors of 0 frame and the first frame, so I can compute coordinates of this vector in 0 frame. Okay. So, but what will happen if I have opposite task? Let us assume that I have some coordinates in 0 frame, and I want to have coordinates in the first frame. So you can guess that please notice that mnemotechnic rule is applied here. P1 transforms from the first frame to 0 frame, and I will obtain coordinates in 0 frame. So if I have coordinates in 0 frame, so I must transform into the first frame, and I will obtain like this. Okay, so please tell me what is the description of this matrix. Can you tell me? Looking at this picture here, here we have matrix R1, 0, and it is described like this. So what is the matrix R0, 1? So what should I do?
Switch ones and zeros?
Yes, exactly. I need to replace 0 and y and 1 in the indices. Yes. So, of course, if you like, you can do it yourself, but by multiplying here the two equations, not by I0, J0, K0, by I1, J1, and K1. And you will obtain this. I will not present just because we haven't got enough time. So we will obtain I0, I0. Here we have I1, J1, K1. Here we have J0, 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 I1, J1, K1, and K0, 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 I1, J1, K1. Okay, fine. So this relationship tells us how to transform coordinates from 0 frame into the first frame. Please notice that the two frames are fixed at the same point, okay? So there is no shifts, they are just rotated somehow. Okay, but what will happen, for example, if I want, for example, move from 0 frame to the first frame and then go back to the 0 frame? So what will happen? So at the first stage, I move from 0 frame to the first frame, okay, and I have a point in the first frame, and I move back to, here is an error, 0, 1. And I move back from the first frame to 0 frame. So finally, I will obtain P0, okay? So I move from one frame to another and go back the same direction. I will write down here I3. What is I3? I3 is identity matrix of order 3, okay? The index means how many items on the main diagonal we have. Because it is valid for any P0, so I can describe that I3 is equal R01, R10, okay? So as you can see, the two matrices R01 and R10 are related somehow. You know from linear algebra, if I multiplied a matrix by another matrix, and I will obtain identity matrix. So how can we call the two matrices?
One is inverse of another.
Okay, one of another is just an inverse. So I can claim that R01 is equal to R10 to like this, okay? Or another 10 is R01 inverse, okay? Why? Because if they will be multiplied, I will obtain identity matrix. Of course, you can, using the same argument, you can write down that R10, R01 is exactly the same. Okay, so what's now? I will back to this, but of course we have quite nice relationship between the two matrices, but I will try to find another nice interpretation. We have 1, 0. So let's compare this matrix R10 with this matrix. Let's try to compare it just comparing appropriate components. So let's start with this component and this component. So what we can say about them?
It's the same scalar.
Yes, exactly. Why? Because as we've noted, we have symmetry of inner product. So this is equal to this. So let's compare this with this. And what? Well, it's strange because here I have J1, I0, and I have quite different. So I cannot claim that they are the same. But I will compare not this by this, but I will compare this and this. Okay, this and this. And as you can see, the two values are the same, arguing as before. If I compare this and this, I can see that they also are the same. So what can I say about this? Can you see? So the rows of this matrix are columns of this matrix. You can compare the other components of the matrices, and you confirm this rule as well. So what is the relationship?
One matrix is transposition of another.
Exactly. Okay, so I can claim that RO1 is R10 transposed. Okay, so I will, and of course, if I transpose this once again, so I will obtain R01 transpose is equal R10 transpose, and transpose are annihilated. Okay, so I will write down once again. So I have R01 is equal to R10 transpose, and R10 is R01 transpose. So as you can see, I've obtained a very nice relationship. RO0 is equal inverse of this, and here is you can see that inverse is equal to transposition. Okay, it is a very rare property. Okay, because probably if I take any matrix, and I try, of course, square matrix, let's say 3 by 3, and if I invert this matrix and take it transposition, probably I will obtain different results. But here, the matrices involved in the matrices composed of appropriate scalar or inner product of appropriate versors have these nice properties. So let's sum up these. So I will call that matrix R belongs to SO3. It is in mathematics and in robotics, it is called special orthogonal group of order 3. Why? Because it works in a 3-dimensional space. And all matrices which belongs to this special space have the following properties. I mean, R multiply, let's say, so the first property is the following. We mentioned this, okay? As you can see, that matrix belongs to this group, whether it has the following properties. So the inverse of this matrix is equal to its transposition, but moreover, determinant of R is equal to +1. So you can ask me why the other property holds here. It is just reflection of right-handed coordinate frames. So let's illustrate this. Please notice that I have I0, J0, and K0. If I multiply I0 by J0, so I rotate this into this, I will obtain what? K0. Probably you should remember the following rule. Please notice that the versors are somehow ordered. I0 is x-axis, J0 y-axis, and K z-axis. And the general rule is the following. I like to write it down in a circle, I, J, and K. Why? Because based on this circular rule, you can easily guess the relationship like this. So if I multiply I0 by J0, I will obtain K0. If I multiply J0 by K0, I will obtain what? I0. If I multiply K0 by I0, I will obtain J0. Okay, so this rule says all of this. Okay, so the rotational matrices which belongs to special orthogonal group are very useful in robotics. Why? Because they allows us to transform coordinates from one frame to another when the two frames are fixed at the same point. Okay, and so let's make a short example. For example, let us assume that someone gives us a 3 by 3 matrix or maybe like this, 1, 0, 0, 0, 0, 1, and 1 here. Oh, like this, okay? And someone gives us this matrix and asks us to answer the following question. This matrix belongs to SO3 or not belongs to SO3. So how can we check this? Okay, the first rule is the following. So the first rule is take inverse of this matrix, take transposition and compare the two, and then compute determinant of this matrix and check this. Of course, it isn't very useful method to check. Why? Because we need to inverse this. So very frequently, instead of this relationship, we try to check the following: RT is equal to R3. It is equivalent to this, okay? But of course, you can see this relationship is much easier to check than this one, okay? Because here I need just to multiply some matrices. So let's check using this rule and check whether this matrix belongs to SO3 or not. So 1, 0, 0, 0, 0, 1, 0, 1, 0. So it is, let's say, matrix A. So I multiply by what? By transposition of this matrix. Unfortunately, the transposition of this matrix looks the same, okay? Because transposition means reflection with respect to main diagonal, and it is the same. And let's calculate this. I take this and multiply scalar. So I have 1, the first row with the second column, I will have 0. The first row with the last column, I have 0. Second row with the first column is 0. Second row with the second column is 1. 0 is 0. Third row and first column is 0. I just compute inner product of appropriate rows and columns. Here I have 0 and 1. Okay, so the first equation is satisfied, but what about this? So I need to calculate determinant of this matrix A. So once again, 1, 0, 0, 0, 0, 1, 0, 1, 0, according to appropriate rule. So I 1, 0, 0, 1, and I multiply this and this with the sign plus, and this and this with some minus. So the determinant of this matrix is equal to what? -1. Okay, as you can see, 1 multiplied by 1 multiplied by 1 is equal to 1, but here we have minus. Okay, so what is the conclusion? This matrix doesn't belong to SO3. Why? Because determinant of this matrix is equal to -1, but it should be equal to 1. Okay. Okay, so please be prepared at the final written test for such kind of tasks. So you will be given a matrix, and you need to compute, to decide whether this matrix belongs to SO3 or not. So you can see it is quite simple. You need to just calculate some data. Okay, but there is another possibility to check whether a matrix belongs to SO3 or not. I will provide you also the second method. So let's call it another method to check matrix belongs to SO3 or not. So let us assume that I have a matrix 3 by 3, and let's arrange it into columns. Let's call the first column N, the second O, and the third A. And A belongs to SO3 when? Maybe. Not quite. Okay. Just okay. Okay, so let's read the statement. If I have a matrix A, if I arrange the matrix into a columns, so it is matrix 3 by 3, so I have 3 columns. I have vector N, O, and A. So if the following conditions are satisfied, what does it mean? The length of the first column is equal to 1, the length of the second column is equal to 1, and the length of the third column is equal to 1. And moreover, if I take cross product of the first and the second column, I will obtain the third column. Okay, so it is another method. Personally, I prefer the first method. Why? Because it is much simpler. Of course, the first three conditions are quite easy to check. Please notice, for example, in here. Okay, so I have the first column like this, the second like this, and the third like this. As you can see, the length of this column is equal to 1, this 1, and this 1. So automatically, the first 3 conditions are satisfied. But this condition is a little bit harder to check. But of course, it is an alternative method to check whether a matrix belongs to SO3 or not. But this relationship tells us a little bit more about the dimensionality of SO3. So our next question is the following. What is dimensional of SO3? So before addressing this question, I need to say a few words about dimensions. So let's go back to the first experiment and the first example with a real line. Okay, so how many data I need to describe uniquely a point on this line. How many data I need? So
1 point.
exactly.
I mean 1 coordinate.
Yes, exactly. I need only a single coordinate. Why? Because if I have a coordinate, if I have a versor, so I can easily establish where the point is. So I can say that dimensionality of real line is equal to 1. If I take plane, so you can easily guess that dimensionality of R2 is equal to 2. And of course, dimensionality of R3 is equal to 3. Okay, so the concept of dimensionality is how many data, minimal number of data I need to describe uniquely an object which lives at some space. So I will try to argue what about dimensionality of SO3. Probably you can help me a little bit. If I have a rotational matrix which belongs to SO3, so it is a matrix 3 by 3, okay? So what is the maximum number of data I have to describe this matrix? You can easily guess that 9, okay? Why? Because the matrix is 3 by 3. But of course, dimensionality of SO3 isn't equal to 9. Why? Because it would be 9 if I can change any data as I like. But of course, if I take, for example, matrix like this, 10, 0, 5, and something like this. So what can you say? This matrix belongs to SO3 or not? For sure not. Why? Because the length of this vector should be equal to 1. But of course, as you can see, it is a little bit bigger than 10, probably. Okay? So the concept of dimensionality is the following. If I have a nine-dimensional object, so I will, and if on this object some constraints are imposed, so each constraint takes us or reduces dimensionality by 1. So let's go back to this. How many constraints we have here? The first constraint is the following. The first column, the length of first column is 1. So it is 1 constraint, okay? The second column length is equal to 1. So it is the second constraint. And the third is here. So we have 3 constraints. And how many constraints we have here? Of course, you can say just a single one. Why? Because I have one relationship. But thinking about this a little bit closer, you can see that here we have 3 constraints. Why? Because the 2 vectors and the third one are 3-dimensional. So here we have 3 constraints here, and also we have 3 constraints here. So finally, I've argued that dimensionality of SO3 is equal to 9, because I have 9 items, minus 3 constraints, the lengthy constraints, minus 3 scalar cross-vector product constraints. So finally we have 3. So as you can see, dimensionality of SO3 is equal to 3, which means that 3 data, minimal number of data, is required to describe a matrix which belongs to SO3 is just 3. Okay, we have 5 minutes more, so I will write down maybe one thing more. So let's make in our example, let us assume the following. I have 0 frame, I0, J0, K0, and I have another frame, but a very special one. So here I have I1, J1, and K1. Okay. So what I have, please notice that the 2 frames are related somehow, okay? As you can see, K1 is equal to K0. So naturally, I can describe that it is rotation about z-axis, here we have x, y, and z, by the angle of, let's say, alpha. Okay. Okay. And right now I will describe the following. Okay. I will describe R10. So let's recall this. I1. K0, K0. Okay, so I just copied the matrix R10, and based on this example, I will try to calculate this. So what is the scalar product of this and this? So can you tell me?
The magnitudes times the cosine between those versions.
It is the length of length of this is equal to 1, so it is just cosinus of alpha. Yes. Please notice that in robotics we frequently used abbreviated form of describing angles. So, for example, C alpha means cosinus of alpha. S alpha is equal to sinus of alpha, just for short. Okay. So C alpha, J1, J0, J1, something, okay, what I have, where I have J1, something is wrong probably here. Oh, of course it is a wrong statement, so don't mind this. I've just copied not this, of course. J, okay. I must correct this. Sorry for the mistake. Finally, probably it will be good. Okay, probably it works here. So nevertheless, here we have right statement. Here J1 I0, so nothing. I will probably stop here because something is wrong permanently. So don't mind. I will go back to this example at our next meeting. Okay. So let's conclude this lecture. We tried to recall some inner product properties, cross product. We established, we worked in a three-dimensional real space. We have the following, we have two frames, 0 and 1, and we established how to transfer coordinates from the first frame to 0 frame, or different way, from 0 frame to the first frame. We established what does it mean SO3. It is special orthogonal group. And we established that dimensionality of SO3 is equal to 3. So 9 minus 3 is equal to 3. And maybe one more. You know from mathematics, what does it mean a group? Yes or not? A group, it is a, but maybe I will continue because we have not time to detail, to give details of this group concept. So probably we will address this question at our next meeting. Okay, there are some questions about today's lecture. I will make the notes in PDF form, and I will send it to ePortal at lecture number 1. Okay, so you can look at them once again. Okay, if there are no questions, so let's meet next week. So see you and bye bye.